Hello everybody and welcome back. I'm sorry I took such a long break. I just got kind of bored with VulnHub and Hack the Box. I didn't really like the kind of style of CTF that I was running into with the full boxes, so while I was gone I just did a lot of programming and stuff and got back into exploit development. So we're gonna go through this challenge, which is ropasaurusrex from PLAIDCTF 2013. And so what this is as you can see, it's a return-oriented programming challenge, and they give you the binary, the libc, and they also tell you how to set it up in a container. So I've already done that. As you can see here, it's running on port 31337. And I've also downloaded the libc and the binary already. So let's jump right into it with a little bit of theory first. So shout out to San Jose University, where I found this slide. So basically, here's the stack, right? And if you have a buffer overflow, you can see we fill the buffer with A's. And then if we want to call a function, we put the address of that function into the stored instruction pointer here. And then above here we'll have the it'll have its argument. So func first takes int y, so that's there. And then once that's done, this will be the next thing it returns to, which will pop the last thing pushed, which is this, off the stack, and return to func second. So you can see how it's like a chain, and then char z will be in place for func second to take as an argument. So what you're doing with the ROP chain is like you're setting up kind of fake stack frames, I guess, in order to pass the right arguments in, and then you use the pop-ret gadget to make sure you're returning to the right spot and getting rid of the previous argument from the stack. Okay, so now that theory's out of the way, we have some more explaining to do. So with ropasaurusrex, ASLR and NX are enabled. So if we I do have ASLR on. If we take this, you can see there's 2 in here. So if it was 0, then ASLR would be off, but 2, so it's on. And now we have to learn a little bit about the procedure linkage table and the global offset table. So the PLT is located in the .text section, which you should know what that is from my other videos. And then the global offset table is located in the .data section. So any call to a function for the first time in a program, the compiler translates to function at PLT. And then that PLT entry for that function has a corresponding global offset table entry, which is jumped to from the PLT. And then from the global offset table, we go back to PLT, which calls a resolver routine, which is the first PLT entry, which places an absolute address for the function in the global offset table. And this happens for every first time you call a function. So like the first time a function is called, the resolver routine will run and give it a global offset table address. So ropasaurusrex, as we said, 32-bit binary, ASLR enabled, and we can't do a simple return to libc, like, you know, put the address of system into the instruction pointer, because we don't know the address of system since the base of libc is randomized. But since the offsets of libc don't change, only the base address, if we know the offset of system and we know the base address of the libc, then we can it'll be the same, like we can still calculate the address of system. And if we take this command and run it a few times, you can see that the starting address of the libc is changing. So ASLR is on. And let's see here. Yeah, and NX is on, so the stack isn't executable. So we know you have to do some ROP. So the first thing to do is to run the program and see what it kind of does. So we have input of some sort. And what we can do is we can try and crash this. And then pipe the output from this into the binary. And we do get a segmentation fault. So we have a buffer overflow of some kind. And now what we need to do, as in the other buffer overflow we did, is find the offset to overwrite the instruction pointer, the stored instruction pointer. So I'm going to use an online pattern generator. And since we used 300 bytes to crash it, we know we don't need any more than 300. So take this, copy. Now I'm just gonna run the binary with GDB. I'm just gonna run it, paste the input, and you can see we have a crash. And you can see this is the value in the instruction pointer. So I think I need to take this, find the overflow offset, and you can see it's 140. So we write 140 bytes into the buffer, and then the next bytes we put in will go into the stored instruction pointer. Okay, so now that we know that, we can start writing our Python exploit. I already have one, but I'm just gonna write the actually, yeah, I'll just use the one I already have. So you can like ignore most of that for now. Here's all you need for now. The host is localhost, the port, the payload variable will have our number of A's, command, so you can ignore all of this, and then we make a socket and stuff like that down here. So I assume you're familiar with socket programming and blah 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 blah, so you can ignore the rest of that for now. So now what we want to do is we have to store our the command we want the program to execute somewhere in the available sections. So if we look at the sections with object dump, we can see what's available to us, and it has to be writable. So anything with the read-only flag isn't an option. So we have all of these, but if you look at the size, you see this one's only 8 bytes for, and the biggest one is .dynamic, so that's probably the best one to use. And then we'll also need this address later as well, so I'm just gonna paste that in here so you can remember it. So that's the address of .dynamic. Okay, and now we can look at the global offset table entries with objump again. So you see we have an entry for write and read, which makes sense because based on what we've seen from the program so far, it's going to use these two functions. So as to what these functions are, if you're not familiar, write, you pass it a Alright, this is the wrong one. We'll basically write, you take a file, you pass it a file descriptor, a destination, and the length of what you want to write. And then read, you pass it the file descriptor that you want to read from, a pointer to the buffer that you're reading into, and then the length of it. So that's that. And then now what we need to figure out is how we can calculate systems address, or calculate the libc address of read with these functions that are available to us. So remember that the offsets don't change. So what we can do is we can use the write function to print read's global offset entry or value to standard output. So these aren't the addresses of the functions in the global offset table. These are just like the offset from the beginning of it. So that'll be our first step to do. Then what we need to do once we have read's address in the randomized libc is to calculate systems address, and systems address in the randomized libc equals read's libc address minus the offset of read to the beginning of libc, and then plus systems offset. So read's libc address in the randomized libc minus the offset of read will give us a starting point of the libc library, and then plus the system offset will give us the address of the system function. We're going to use a tool called ROP gadget to locate the available gadgets for us. And we need 3 pops and a ret, because both functions we're going to use take 3 arguments, meaning we need 3 pops to get them off the stack. I think this is how you do it. Oh, hang on. Binary. And there we go. And right away I see one. Pop, pop, pop. Oh, that's 4. Here we go. Pop, 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 ret. So you can take note of this address. Keep that. So this is what we'll use. We only need really 1 gadget. And then the next step would be to, so you have to find the call address of read, so we can actually use that. So we're just gonna ob jump and pipe the output to grep. And you can see this is it right here. Read at PLT. So we'll save that in here. And now we need to find the offsets of read and system from the start of libc. So if I go to where I had the libc, and then grep for read, whoops, sorry. You want to look for the one that's just like the plain old read function with the sockets. So like not whatever this is. And this looks like it, so here's the offset. We'll take this, put that in here, and then the offset for system, let's do the same thing. And you can see this is it right here. So we'll take that and store that here as well. And now, knowing all of this, we can really look at our exploit here. So again, I have the host, the port, the 140 A's, the null terminated command passed from CLI arguments, and then I have the read libc offset and the system offset. And now what we want to do is we want to write our command this into .dynamic. So this just means unsigned integer and little endian. There are plenty of articles about that, blah, blah, blah. So here's the address of read that we got. Where is it? Here. So we're gonna call read, and then what it'll return to is this should say pop 3 pops. We're gonna return to that gadget whose address we also have here, and then and then the arguments for read. So 0 is the argument for standard input. The address of .dynamic, I think we put down, yeah, right here. And then the length of the input, we're just going to use the length function in Python for figuring out the length of this. And then we need to leak the address of read in the global offset table. So we use the address of write, which we figured out earlier. Then we once again have our pop ret gadget, and then 3 arguments, 1 for standard output because we want to print the address of standard output. The second argument is the address of read's global offset table entry, which we calculated looking at this, or we didn't calculate, we just looked at it. And then the length of the address, 4 bytes. And then what we're going to do is the next part of the chain will call read to overwrite its own global offset table entry with the address of system. So we have the address of read. We have the gadget again for the 3 arguments, 0 for standard input. And then this right here is this exact same line. So this will be the read's global offset entry, and that's what we're going to overwrite, and then the length of the address that we're going to send as well, which will be system's address. So this is like the destination of where we're writing to, and then this is the length of system's address. Now we call system. So at this point, it'll be overwritten with the address of system in the randomized libc. Since this is the last part of the chain, we don't need a valid return address. So we don't need the gadget or anything. So we can just put a bogus return address in. And then we need to pass the argument to system, which is the command that we put in .dynamic. So which is just this line here again. And then we make our socket, we connect, we send the whole payload, and then it'll be waiting, so we send the command, which will go in .dynamic. And then we'll receive, it'll write to standard output the address of read, and then we'll print that out, so we'll leak the address. And then from that, we'll calculate the address of system with the newly acquired address of read in the randomized libc minus the read libc offset plus the system offset, which we calculated up here. And then we'll print libc systems at here. And then we'll send the the address of system to be overwritten in the global offset table. And that's pretty much it. So hopefully you follow along. I gotta admit, it took me a while to understand this, but let's see if we can run this and get it working. And there we go, it does work. So you can see it leaks our read address, and then we calculate system, and we send it the command, and it executes. So you can play around with it. So yeah, that's pretty much everything. If you have any questions, leave a comment and I'll do my best to answer. This is a pretty new concept to me too, so sorry if my explanations weren't completely perfect. Feel free to correct me in the comments as well if I said something that was technically incorrect. And other than that, I'll see you guys next time, probably with, I don't know, a similar video. We'll see.